board.
I figured it out.
Okay, matrix. Not the one with this guy. Has nothing to do with that. All right, so first, what is a matrix? A matrix is an array of numbers. It's often two-dimensional. Everything that we talk about today is going to be about two-dimensional matrices. So this is an example of a matrix. A matrix, this matrix has 2 rows, 3 columns. So we call that a 2 by 3 matrix. And we can refer to the elements individually with indexing. It's 0 indexed, like arrays, and really this is just a two-dimensional array. So this is how we would represent it in code, with just a two-dimensional array, or arrays within an array. Okay? So we can refer to the element A00, for example, and that's the number 6 in this matrix A. So we refer to the row index first and the column index second. So the number 1 is in the position 0, 1, and the number 4 is in the position 1, 1. I'm sorry. The number 4 is in the position 0, 1. So it's the 0 row in the first column. The negative 9 is in the second row, so that's index 1. In the second column, so that's index 1 for the column, 1, 1. So we're used to 0 indexed arrays at this point, hopefully. So it's the same concept there, but now we're keeping up with a row and a column, which can get to be, a little bit confusing for some people, particularly people like me who are spatially challenged. I'm definitely spatially challenged, so I have to really think about it to get the numbers right. So if that's true for you, don't feel bad. So why do we need to know about matrices? Well, they're really useful data structures. We'll use them all the time. You've probably used two-dimensional arrays at least a few times. They come up all the time. And in some cases, it's useful to do matrix mathematics. So doing addition or subtraction, multiplication, dot products. We'll do this in order to solve problems. Sometimes it's the most elegant way to solve a problem is using this type of data type and the data structure and using those types of operations. So one example that we'll look at again later in this presentation, we'll walk through it, is if we have items that have different, different styles or different sizes of an item. They'll each have a different price, and calculating the total sales over some period of time would involve matrix math. We would use the dot product to do that. So we'll look at that example at the end of this presentation. So let's start with addition. Addition is pretty straightforward. In addition, we first of all require that the two matrices that we're adding together are the same dimensions. They have to have the same number of rows and columns. Otherwise, it doesn't work. Okay, so that's the first requirement with addition. And then all that we do is we add up the elements that are in the same position in each matrix, and then we put their sums in the result matrix. So in the example here, the 3 is in row 0, column 0 in the first matrix, and the 4 is in row 0, column 0 of the second matrix. We add those two together, we get 7, and we put that in row 0, column 0 of the result matrix. Okay? And that's all we do. We just add each element in each position and then put the sum in the result matrix in the same position. Does that make sense? That's pretty straightforward. Likewise, subtraction is exactly the same. So with the subtraction, just like with addition, and really, when you study algebra, you really realize that addition and subtraction are the same thing. Subtraction is just addition with negative numbers. But we do the same operation, so we have to have the matrices that we're subtracting have to be the same dimension, same number of rows and columns, And we do exactly the same procedure. We take the 0, 0 element of the first matrix and the 0, 0 element of the second matrix. The order matters here with subtraction, just like it does with regular numbers, scalar numbers. So if we're saying A, we're subtracting B from A, if A is on the left side, then when we look at each element, we're saying, for example, with the 0, 0 element, 3 take away 4, and that result is -1. If we reverse these two matrices, if we had B take away A, then the result would be different. Okay? Then we'd be saying 4 take away 3, and that result would be 1 and not -1. So with subtraction, we have to consider the order that the two matrices are in on the left side of the equal sign, and we have to do the subtraction honoring that order. Okay, does that make sense? So that's pretty straightforward too, so far, not too bad. Scalar multiplication is also pretty straightforward. Scalar multiplication just means that we're multiplying by a scalar value or a constant or a plain old number. Okay, so we're taking a number and we're multiplying that number by each element of our matrix. And that's exactly what we do. And then we put the result of that multiplication in the correct position in the result matrix. So the 4 is in the 0, 0 position in this matrix. We multiply that by 2. That answer is 8, and we put that in the 0, 0 position of the result matrix. And then we multiply the 2 by 0, which is in the 0, 1 position of our matrix, and that gives us a result of 0, so we put that in the 0, 1 position in the result matrix. Okay? Everybody following along so far? It's not too bad at this point, right? So it's just like basic addition, subtraction, and multiplication at this point. But this is where it gets confusing. So the dot product is when we multiply two matrices by each other, okay? And then what we do is we find something called the dot product. To find the dot product, we multiply the elements of each row of the first matrix. Again, the order of what's on the left side of the equal sign matters here, okay? So the first matrix, the one on the left side of the multiplication, we take each row of the first matrix and multiply it by each column of the second matrix. So what that means is that the result is going to have the same number of rows as the first matrix and the same number of columns as the second matrix. So in this example, we take the row, this matrix only has one row, okay? It could have more though, we'll look at some more examples. And we multiply the first element of the row by the first element of the first column. So 3 times 13, and then we add to it the second element of the first row times the second element of the first column. And then we add to that the third element of the first row by the third element of the first column. So 3 times 13 plus 4 times 8 plus 2 times 6. And that sum gives us the first element of the result matrix. So to do the dot product, we have to do multiplication and addition to get each value in the resulting matrix. Okay? So to get the 63, what did I have to do? Three times 9 plus 4 times 7 plus 2 times 4. And that gives me the 63. To get the 37, what did I have to do? Three times 7 plus 4 times 4 plus 2 times 0. And that gives me the 37. And to get the last element in my result, I take the row and multiply it by the last column. So I have 3 times 15 plus 4 times 6 plus 2 times 3. And that gives me the 75. Okay, so it is a little bit tricky, and you just have to do it slowly, or write a program that does it for you. Okay, so we'll have a morning challenge where you can do that. All right, you just have to take it slowly and do it one step at a time. Okay, you will have to do matrix multiplication on the maths test, the dot product. You can write a program that does it for you. If you write the program, then it's fair to use it on the test, because if you write the program, it means you understand how to do this. Yes? Okay? So that's my suggestion about understanding this, is write a program that does it, because in that process, you're going to learn how to do this if you don't know how to do it already. Okay? So let's look at some more examples. So you might be able to tell with that example that in order to do a dot product, the number of columns in the first matrix must be equal to the number of rows in the second matrix. Does that make sense? Because we're going to multiply row by column, and we have to have the same number of elements in a row in the first matrix as we do in a column of the second. Does that make sense? But it doesn't mean that the number of rows in the first matrix is equal to the number of columns in the second matrix. It is in this example, but it doesn't have to be. Like in the first example we just looked at, we only had one row in the first matrix, and we had 4 rows in the second one. In this example, we have 3 rows in the first matrix, and we have 3 rows but 1 column in the second matrix. So what matters is that we have the same number of rows in the first matrix as we have, the same number of columns in the first matrix as we have rows in the second. That's what matters, and that's what you have to check for. Okay, so when you write an algorithm to do the dot products, you need to make sure that the matrices meet that constraint.
I was just going to say, it makes it easier for people. When you refer to matrices, you refer to like a 3 by 3 or a 3 by 4, right?
Yes.
You just put them next to each other in your head, and as long as the 2 middle numbers are the same, you can do it.
Yeah, that's a good way to think about it, Matt. That's a good way to think about it.
What you're left with is the 2 outer ones is what the result is.
That's right. So this matrix is a 3 by 3, right? And this is a 3 by 1. So the 2 middle numbers are 3, right? This one is a 2 by 3, and this one is a 3 by 2. So as long as the 2 middle numbers are the same, then you can do the multiplication.
And you're left with the 2 by 2, which is the 2 main numbers,
And the 2 outer numbers. Yeah, that's right. That is a good trick. So let's look just again at another example, and we'll do at least one of these on the whiteboard too to make sure that it's clear. So in this example, the first step is we multiply the first row by the first column. And then you're going to multiply that row by every column that's in the second matrix, okay? So we can have any number of columns in the second matrix. You just have to multiply each row by every column. So we multiply the 1 by 7, we add to that 2 times 9 and 3 times 11, and we get 58 for the first result. And then we multiply the first row by the second column. So 1 times 8 plus 2 times 10 plus 3 times 12, and we get 64 for the second result. And then finishing up that one, once we've done all the columns multiplied against the first row, we go to the second row. We do the same thing. If we had more rows here, then we would continue to do that. Okay? So 4 times 7 plus 5 times 9 plus 6 times 11 gives us 139. And that goes in the result here in the first spot in the second row, because we're multiplying by the second column at this point. And then 4 times 8 plus 5 times 10 plus 6 times 12 And that gives us 154, which goes in the last spot in the resulting matrix. Okay? Yes?
What happens if the ratio don't sync up? Like you've got a 2 by 3 and a 4 by 4.
Then you can't multiply them.
So what do you do then?
You don't multiply them. Yeah, so just like with addition and subtraction, they have to be exactly the same dimensions, or you cannot, it's not a valid operation, basically. It's only a valid operation if that's true. Yes,
When you
Anthony?
represent it as a nested array, are the elements grouped by row?
Yeah, so the first element of a nested array would be the first row. The second element would be the second row. Yeah. So each array is a row inside of that nested array.
Okay.
Yeah. Okay, so sometimes, depending on the problem, we can get around, it may be that we have like a 2 by 3 and a 2 by 3. We can't multiply those, a 2 by 3 and a 2 by 3, because we have 3 columns in the first array and 2 rows in the first matrix and 2 rows in the second matrix, and we can't multiply those. Sometimes, depending on the problem, we can transpose one of the matrices and do a valid multiplication, but you have to understand what that data is representing. So we're going to look at an example in a minute. So transposing a matrix is turning the rows into columns. Okay? So if we have this matrix here on the left and we transpose it, the first row becomes the first column. The second row becomes the second column. Okay? That's transposing. And we've just turned a 2 by 3 matrix into a 3 by 2 matrix. All right?
Is transposing always done in that direction? Always or is there different operations that flip it?
It's always done in that direction.
The first row is the first column.
The first row becomes the first column.
So you just run it more times if you want to get the different figure.
Yes, so if you,
If you just run the same operation, you end up with
you're going to end up with the same thing. So if you transpose this one, the first row is going to be the first column. The second row is going to be the second column. The third row is going to be the third column. Right? You're going to end up back here.
Would you?
Yeah.
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 So 6-1 is the first row. It would become the first column. 6-1.
Oh yeah.
Hmm. So it would have to be some other type of operation you did if you wanted to flip it, if you wanted to like mirror it and then transpose it, yeah. But transposing always looks like this.
It's probably the rest is arbitrary anyway, really, so.
So let's look at an example. So say we have a shop that sells 3 kinds of t-shirts. So we have style 1, style 2, and style 3. And they each have a different price. Okay? And then let's say over 5 days, we make these sales. So we have number of shirts sold and type of shirts sold. So we could say that this is one matrix, the price matrix for the different styles, and this is another matrix, which represents the data of sales over a 5-day period of each one of those styles. So how can we calculate the amount of money made on each day? This is definitely an example of where we would use matrix multiplication. That's what we're doing here. You might think about it a different way, but what we're doing here is matrix multiplication. Okay? So the way that it's set up right now, though, if we represented exactly what we have in this table as a matrix, it would look like this. It would be a 5 by 3. A 5 by 3 matrix, yeah? And if we wanted to multiply it by our price for style matrix, we can't do it like this. And why doesn't this work?
Or is it columns don't match?
Yeah, because we've got 3 columns, but we have 5 rows, right?
Somewhere transposing that.
If only. If only there were. So we can't do it in this form because the number of columns in the first matrix has to be match the number of rows in the second. So we can transpose the daily sales matrix, and we're still going to end up calculating the number that we want. That's what you have to understand, though. You can't just sort of willy-nilly transpose matrices and assume that you're getting the result that you want. But yeah.
So essentially, you only really need to transpose when you screwed up your data structure.
Yeah. So, look, the way we choose to represent our data, it might make sense to do it the way we did initially because we're thinking, okay, we're going to put the styles across this way and the days down this way, but we could just as well, right, put the styles down as rows and have columns for the days. But maybe the way that we think about the problem first, we think about it this way. That's the way I thought about it. So that's the way that I represented the data at first. But then when I realized what I need to do with that data, then I realized, okay, that's actually not the best way to represent it. Because in order to do this operation, I need to represent it a different way in the opposite dimensions. So if we transpose this data, which is really just like writing what I said, putting the days as columns and the styles as rows instead, which is transposing a matrix. That's all we're doing there, is transposing the matrix. So now we've got the styles as rows and the days as columns. And when it's in this form, we can do matrix multiplication on it. Right? So now this first column represents what? What does this represent? If we just look at Monday. It's the sales that we made on Monday, where the first row represents style 1. So we're going to multiply that by the cost for style 1. The second row represents style 2, so we're going to multiply that by the cost for style 2. And the third is 3, and multiply it by the cost for 3. And we're going to add those together to get the total sales for the day. Right? And we do that all the time. We don't think of it as matrix multiplication, but that's what we're doing. Okay? So we do our matrix multiplication to get the sales for each day. So this number represents the total sales for Monday. Yeah? And this number represents the total sales for Tuesday and for Wednesday and for Thursday and for Friday. So hopefully that example helps to make sense of it. It does for me. So with matrix multiplication, even though I've done plenty of it, just because I'm sort of spatially challenged in my brain, it is hard for me to think about it abstractly. I have to think about it with an example for it to make sense. Yeah?
Instead of transposing the larger array, would it have been possible to transpose the small array and swap it, or would that give you different numbers?
So let's think about it.
Yeah.
Okay? So first of all, we only have 3 different t-shirt styles, right? So transposing that array isn't going to help us, is it?
No.
So you will get a different result though. Say you have 2 arrays that are the same dimensions. Transposing one and doing the multiplication versus transposing the other and doing the multiplication will give you 2 different results.
Yeah.
So you really do have to understand what data are you representing and what are you trying to do. Okay, that's important to understand. All right, so this is a challenge that you can do later. I'm going to give you a morning challenge for the multiplication one, okay? But you can start by writing a JavaScript. Write it in JavaScript since you started JavaScript. Write a function in JavaScript that takes 2 matrices as input and does the addition. So you want to make sure that your function checks the dimensions of those matrices, before you try to do the addition, and you want to return something like nil or something like that if the dimensions aren't valid. And if the dimensions are valid, then you'd want to return the sum of those two matrices. And then maybe tomorrow, I can't remember if I've already created a JS challenge for it or not, but I'll give you a challenge for writing a function that does matrix multiplication, that does the dot product, so you can make sure that you really understand how that works. Now, shall we do some on the board, or do you guys feel comfortable with that multiplication? Does somebody want to get up and try to do one on the board? I put one up here. We'll do small numbers so you don't have to do like big calculations in your head. Yeah?